The last lesson of this set of podcasts is the reactions of alkynes. And they are very similar to the reactions that we've learned of alkenes. So we'll go through them in order. And I'll use propine because it's easy to draw. I'm going to treat it with HCl. Now, if I only use one equivalent, 1 mole of HCl for 1 mole of propine, I can control it fairly well. I don't know. I've actually never done it, but I'm doing it on paper. And I will make this structure here. It follows Markovnikov's rule, where the H goes to the outside and the Cl goes to the inside. Now, if I put lots of HCl in there, so HCl in excess, what's going to happen is, once again, the H will go to the outside and the Cl will go to the inside. And we'll end up with this dichloro compound, very similar to alkenes. Now, again, if I take my 1 propine and treat it with bromine, we're going to assume this is in excess. I will end up with complete bromination, which for some reason makes everybody laugh when I say that at school. Now, there's another reaction that we didn't talk about for hydration. You can do this with alkenes too, and it's usually a little bit less harsh than just dumping in H2SO4. You're going to have to use mercuric or mercury 2 sulfate with H2SO4 as your catalyst. Now we're getting to the point why organic drives people nuts, is that you have to memorize things. But let's just look and see if we can avoid some of the memorization. So what we're doing is we're going to hydrate, add water across the triple bond. When we do that, we just need to add an extra catalyst, this mercuric sulfate with H2SO4. Don't worry about a mechanism here, just understand that it follows Markovnikov's rule. Now, when you're done with Markovnikov's rule, we add an H to the outside and an OH to the inside. Now, this is the interesting part. This is an enol. Enols aren't stable. They quickly rearrange to move the double bond and the hydrogen to form a ketone. These kind of isomers are called Tautomers. They differ in the placement of a double bond and an H. Now, I like to draw the mechanism of this just to understand what's going on. So the pi bond here in the enol breaks and picks up the proton, and the double bond is formed from these electrons going here. So we have enol and ketone equilibration. On the same vein, if you use hydroboration followed by oxidation, which was the anti-Markovnikov way of adding water, we take our propine, treat it with borane, followed by H2O2 in basic solution, we're going to end up with this enol. And remember, enols don't last. The equilibrium lies far toward the double bond O. And you end up 1, 2, 3 carbons. The O is on the end, so you end up with an aldehyde. Now, the last reaction is one in which we look at the acidity of the terminal H. So if we look at an alkyne, and I'm actually going to, instead of drawing, I'm just going to draw out the H right here. So there's an H attached here. This is actually a fairly acidic H. It doesn't seem acidic. It has a pKa of 25. So compared to acetic acid, it's not very acidic. But if I can treat it with NH2 from sodium amide, which is our strongest base that we use in organic chemistry, at least the one that I use, what's going to happen is, let's do an acid-base reaction. You end up getting a minus charge on this alkyne and NH3. If we review our acid-base chemistry, this has a pKa equal to 36. So the equilibrium lies this direction. So NH2 minus can pull off this proton. In itself, this is not that interesting of a compound. But if we take this negatively charged propyne and then treat it with a compound such as ethyl bromide, what happens is we have a substitution reaction. And you can actually extend the carbon-carbon chain. So we start with propyne and we end with 2-pentyne. And that's really significant because we have formed a new carbon-carbon bond, and it's not very easy to do that.